Hi, in this module we are going to discuss about biodegradable films and their degradable mechanisms. Hope you have enjoyed the previous modules on bio nanopackaging in food packaging applications. In this module, I am going to share my knowledge on the biodegradable films and their degradation mechanism. As we discussed in the previous module, biodegradable films are viewed by the research scientists as an alternate to the various synthetic polymers based packaging material used for food packaging applications. In this aspect, this particular topic on biodegradable films and their degradable mechanism is considered as more relevant and important topic for today's discussion. Biodegradable films and their degradation mechanism. In recent years, there has been a marked increase in interest in biodegradable materials for use in packaging, agriculture, medicine and other areas. Plastic films are often criticized because they are seen as disposable products which once disposed of do not biodegrade. In the past 20 years, the production and the use of plastic have been enormously increased. Most of today's synthetic polymers are produced from petrochemicals which are not biodegradable. Persistent polymers generate significant sources of environmental pollution, harming wildlife when they are dispersed in the nature. Worldwide statistics shows that 43% of marine mammal species, 80% of sea turtle species and 44% of sea bird species are susceptible to ingesting marine plastic debris. Further, to add an important statistics on this topic, I would say that the plastic film production has increased from 0.5 to 260 million tons per year since 1950. 40% of plastics produced every year are discarded into landfill. Every year, more than 500 billion plastic bags are distributed and less than 3% bags are recycled. They are typically made of polyethylene and can take up to 1000 years to degrade in landfill that emit harmful greenhouse gases. Now, how to get rid of this problem? Immediate solution to this problem that could strike the minds of nature lovers and the scientists may be, why can't we use something for the production of plastic film that would be biodegradable in nature? Recent advances in the plastic film technology now allow the production of a range of plastic films which are degradable, biodegradable or compostable. The term biodegradable material is used to describe those materials which can be degraded by the enzymatic action of living organisms such as bacteria, yeast, fungi. The ultimate end products of the degradation process includes carbon dioxide, water and biomass under aerobic conditions. While in case of anaerobic conditions, the end products that are obtained include hydrocarbons and methane. Polymers form the backbone of the plastic material. As a result, many researchers are investing time into modifying traditional biopolymers to make them more user friendly and into designing novel polymer composites out of naturally occurring materials. A number of biological materials may be incorporated into biodegradable polymer materials, with the common being starch and fiber extracted from various types of plants. The belief behind this type of production of biopolymer film is that biodegradable polymer materials will reduce the need for the synthetic polymer production, thus reducing pollution at a low cost, thereby producing a positive effect both environmentally and economically. Dear students, though the use of biodegradable film based packaging concepts seems to be attractive, this particular technology has certain limitations. If you look at the primary purpose of plastic packaging film used in food packaging, it is and contain the food as such and expected to be durable enough to perform this function. In contrast to this requirement, biodegradable plastic is designed to break down. Making a packaging material biodegradable therefore might solve the waste issues at the end of the material's life, but this particular feature of the material makes the packaging unable to properly protect a product. As a result, that particular product may get spoiled, creating a great negative impact on the food product and to the environment. In addition to this, the speed at which a biodegradable packaging breaks down is dependent on exposure to light, heat and oxygen. As this exposure could vary dramatically, the shelf life of the biodegradable packaging films cannot be precisely predicted. Students, I am now often telling the term biodegradability. Let us see what is biodegradability. The American Society for Testing of Material (ASTM) and the International Standard Organization (ISO) defines biodegradable plastic as those which undergo a significant change in chemical structure under specific environmental condition. These changes results in loss of physical and mechanical properties as measured by the standard methods. Plastics may also be designated as photodegradable, oxidatively degradable, hydrolytically degradable, or those which may be composted. These polymer materials are designed as that of a composite, where a polymer matrix, that is the plastic material, forms a dominant phase around a filler material. The filler is present in order to increase mechanical properties and decrease material cost. Do we have place for this type of biodegradable packaging material in food packaging? As you all aware that food packaging is becoming increasingly important in food industry, where advances in functionality such as convenience and portioning are gaining more attention. Furthermore, there is also an increased awareness on sustainability which can be achieved on different levels. On the level of raw material, use of recycled materials or use of renewable resources are two strategies to reduce carbon dioxide emissions and the dependency on fossil resources. On the level of production process, business people are looking for more energy efficient process. In terms of water management, this is another level where efforts are made to reduce and recycle the used material, in addition to encourage the use of biodegradable and compostable packaging materials, food packaging. These measures are expected to reduce the municipal solid waste problem. With respect to the above sustainability concept, in the last decade, there has been an increased interest from the food, packaging and distribution industry towards the development and application of bioplastics for food packaging. Biodegradable products are mainly produced from biopolymers. Biopolymers are used in packaging material, that is, it is used for making the trash bags, wrappings, loose film foam, food containers, film wrapping, laminated paper, as well as it is also used as a disposable non-wovens and hygiene products, consumer goods and agricultural tools. How these biodegradable polymers are classified? We have a vast number of biodegradable polymers such as cellulose, chitin, starch, polyhydroxyalkanoates, polylactide, polycarbolactone, collagen and other polypeptide. These polymers have been synthesized or they have been formed in natural environment during the growth cycles of the organisms. Biodegradable polymers are often classified according to their synthesis process into four categories, such as polymers from biomass, such as agropolymers from agro resources, polymers obtained by microbial production, polymers that are conveniently and chemically synthesized from monomers obtained from agro resources, and the last category of polymer is obtained from fossil resources. Further, from the classification shown in the figure, it is clear that agropolymers are further classified into polysaccharides and protein. Gums and chitins are polysaccharide based. PHA, that is polyhydroxyalkanoates, is a best example for microorganism based. while polylactic acid, that is PLA, are synthesized from the bio-derived monomers polycaprolactones PCl, polyestramides PEA, are synthesized from oil-based synthetic monomers. According to the statistics, biodegradable films made from rice starch shows potential for use as a packaging material. However, compared to common thermoplastics, biodegradable rice starch films still reveal some disadvantages such as low mechanical properties and lack of efficient barrier against polarity compounds. This constraint has led to the development of the improved properties of biodegradable film from rice starch by modifying its starch properties and or incorporating other materials. Chemical treatments and physical treatments in combination with other biodegradable materials and fiber reinforcement could improve the properties of biodegradable film made from the rice starch. Let us see what are the different types of biosources we have for the production of biodegradable films. First and foremost in the category is starch. As everybody knows that starch is a major storage form of carbohydrate in plant. It consists of two components. One is amylose and the linear straight chain, and the other one is amylopectin, which is a highly branched component. Principally, there are three ways by which the starch can be used for the production of biodegradable polymers. The first one is the preparation of starch composite with other plastics with a low amount of starch. The end product thus obtained will have enhanced biodegradability compared to traditional oil-based polymer material. The second way of starch application is the preparation of starch composite, which with the starch content being more than the half by mass. And the third way of starch biodegradable polymer preparation uses the extrusion processing of mixtures of granular starch. Now let us see the second bioresource which is available for the preparation of biodegradable films. It is nothing but cellulose. The cellulose is the most widely spread natural polymer derived by delignification from wood pulp or cotton linters. It is a biodegradable polysaccharide soluble in a mixture of sodium hydroxide and carbon disulfide to obtain cellulose xanthanate and then recast into an acid solution, that is usually the sulfuric acid, to make a cellophane film. Another method of production of cellulose derivative is derivatization of cellulose from the solvated state via esterification or etherification of hydroxyl groups. Now the final third important bioresource that can be used in the biodegradable film production is pectin. Pectin is a linear macromolecule consisted of alpha-1,4 linked D-galactouronic acid. This monomer unit could be partially replaced by alpha-1,2 linked L-rhamnose, leading to a new structure named rhamnogalactourine. The third pectic structural type is rhamnogalactourine 2, which is a less frequent but complex and highly branched polysaccharide. Chitin and chitosan. Chitin is the second most abundant acropolymer produced in nature after cellulose. It appears in nature as ordered crystalline microfibril forming structural components in the exoskeleton of arthropods or in the cell walls of fungi and yeast. It is biodegradable, non-toxic and readily biocompatible. It is stated that chitosan is a promising biopolymer for active food packaging. Its sensitivity to moisture can be offset by blending it with cinnamon oil, that is CEO, fish and poultry. Many researchers revealed that a unique compatibility can be achieved between chitosan and cinnamon oil. The incorporation of cinnamon oil improved the antibacterial properties of chitosan. Films containing cinnamon oil are useful for coating of highly perishable food such as fishes. Nanotechnology in biodegradable polymer production. Now let us Nanotechnology is generally defined as the creation and utilization of structure with at least one dimension in the nanometer length scale, that is 10 to the power minus 9 meter. These structures are also called nanocomposites and could exhibit modification in the properties of materials or create novel properties and phenomena to the material. To achieve these modification, a good interaction between the polymer matrix, that is the continuous phase, and the nanofiller, that is the discontinuous phase, is desired. When bioplasm mixed with the nano clay particles, the resulting nanocomposites exhibit improved barrier properties compared with the poor bioplastics, and after their useful life can be composted and returned to the soil. The clay has a unique morphology that contains one dimensions on the nanoscale. Nanoscale composites have been developed for potential use in a variety of food packaging applications, and some products are already available for the consumer. Dear students, apart from packaging material, biodegradable films have lot of other applications too. Now let us see what are all they. Application in agriculture. In agriculture, biodegradable films have found three major applications. They are: one is covering film in greenhouses, second one a mulch film, and third is the controlled release material for fertilizer. Starch-based material can be used as covering for various structures used in agricultural activities. After using, starch-based films can be plowed into the soil and disposed directly. The major benefit of this activity is no toxic residue formed after the degradation of the starch-based biodegradable polymers. Utilization efficiency of fertilizers is another key element of the development of agriculture productions. However, structures used in agricultural activities, due to surface runoff, leaching and vaporization, the fertilizer escapes to environment, thereby reduces the agricultural yield and also creates environmental problem. Now, the invent of biodegradable film facilitate the release of fertilizers slowly or in a controlled way. As a result, the loss of fertilizers and environmental pollution can be avoided or reduced. Thus, the development of starch-based materials for agriculture application is being continued. Biodegradable polymers have been widely investigated in bone tissue engineering. Starch-based biodegradable bone cements can provide immediate structural support and degrade from the site of applications. Moreover, they can be combined with bioactive materials which allow new bone growth to be induced in both the intersurface of cement bone and the volume left by the polymer degradation. In addition, starch-based biodegradable polymers can also be used as a bone tissue engineering scaffold. Starch-based biodegradable polymers in the form of microsphere or hydrogel are suitable for drug delivery. There is no need for surgical removal of the device after drug depletion. The unique properties such as hydrophilicity, permeability, biocompatibility, and to some extent similar to soft biological system of starch-based hydrogel makes them useful for various biomedical applications. The 3D structure of starch-based hydrogels enables them absorb and reverse plenty of water and keep good enough mechanical property at the same time. Starch-based hydrogels have received growing interest for biomedical applications. With PVA and starch with PVA hydroxyapatite hydrogel are obtained via repeated freezing and thawing cycles, and hydroxyapatite HA can be well dispersed in such a matrix. The water content in the fresh starch GPVA HA hydrogel is comparable to that of PVA HA hydrogel, and the tried starch GPVA HA films can reabsorb water soon and reach swelling equilibrium within 12 minutes. Let us consider the preparation of rice starch based biodegradable polymer film preparation. Formation of any biofilm requires the use of at least one constituent capable of forming a matrix with adequate continuity and cohesion. Generally, this is composed of polymers or compounds which under the preparation condition are used to form continuous crystalline or amorphous products. In the case of coating, for which film system can be applied directly to the product, two forces are relevant, that is between the molecules of the coating material is called cohesion, and that between the coating and the support structure often called as addition. The degree of cohesion produces the barrier and mechanical properties of the film. High structural cohesion is manifested by a reduction in the flexibility, porosity and permeability to gases and solutes. The degree of cohesion depends on several factors. They are the chemical structure of the film material, the presence of plasticizing and cross-linking agent, the nature of the solvent used in its dilution, the method of application, and the remaining are the procedure used for removal of the solvent, the final thickness of the film. The highest cohesion is generally obtained for ordered polar polymers with long chain which were precipitated in crystalline form. The cohesion of film generally increases in proportion to their thickness up to a threshold beyond which it remains constant. The speed of evaporation of the solvent and or excessive temperature makes manifested by inadequate cohesion on account of the premature immobilization of the polymer molecule. Regarding the addition of the coating to the food surface, this is generally facilitated by hot application. The formulation of films may require one of the following method. The first method is casting. The casting process consisting of drying a solution or a gel. This method is considered as a simple method for producing films with controlled thickness. This method is also used for food coatings as well as for non-food applications. In this method, gelled coating material is prepared as a hot solutions and the product is dipped in the solution. A protective layer is formed on the surface upon cooling. The second method is extrusion or thermopressing process. In this process, material is pushed or drawn through a die of a desired cross section. The two main advantages of this process over other manufacturing processes are its ability to create very complex cross sections and work materials that are brittle because the material only encounters compressive and shear stresses. It also gives finished parts an excellent surface finish. And the third one is electrohydrodynamic atomization, that is EHDA, referred to as electrostatic atomization or electrospraying. This is a process in which a liquid is forced through a capillary and a potential difference of the order of kilowatt is applied between the capillary and the collection electrode. EHDA can be performed in various modes, but the staple cone jet mode is the most desirable as it provides near monodispersed droplets of a few micrometers in size. The droplet size can be controlled by the flow rate and applied appropriately. Now let us see the mechanism and methods of degradation of the biodegradable film. Breakdown or degradation of a polymer materials may occur by three ways. It is due to the microbial action, or it may be due to the photo degradation, or it may be due to the chemical degradation. All the three methods are classified under biodegradation as the end products are stable and found in nature. Many biopolymers are designed to be discarded in landfill, compost or soil. The material will be broken down provided that the required microorganisms are present. Normal soil bacteria and water are generally all that is required, adding to the appeal of microbial reduced plastics. Polymers which are based on the naturally growing materials such as starch or flax fiber are susceptible to degradation by microorganisms. The material may or may not decompose under aerobic conditions depending on the formulation used and the microorganisms required. In case of material where starch is used as an additive to a conventional plastic matrix, the polymer in contact with the soil and or water is attacked by the microbes. The microbes digest the starch, leaving behind a porous sponge-like structures with a high interfacial area and low structural strength. When the starch component has been depleted, the polymer matrix begins to be degraded by enzymatic attack. Each reactions result in the scission of molecules, slowly reducing the weight of the matrix until the entire material has been digested. Another approach to microbial degradation of biopolymers involves growing microorganisms for a specific purpose of digesting the polymer material. This is a more intensive process that ultimately costs more and circumvents the use of renewable resources as biopolymer feedstocks. The microorganisms under consideration are designed to target and break down petroleum-based plastics. Photodegradable polymers undergo degradation from the action of sunlight according to ASTM 883-96 procedure. In many cases, polymers are attacked photochemically and broke down into small pieces. Further microbial degradation must then occur for true biodegradation to be achieved. Polyolefin. It is a type of petroleum-based conventional plastics and are polymers found to be the most susceptible to photodegradation. Photodegradable biopolymers are developed by incorporating additives that accelerate the photochemical reactions. The additives best example is benzophenone. Modifying the composition of the polymers to include more UV absorbing groups, that is carbonyl, can be added, synthesizing new polymers with light sensitive groups. An application for biopolymers which experience both microbial and photodegradation is in the use of disposable mulches and crop frost covers. Some biodegradable polymers material experiences a rapid dissolution when exposed to particularly chemical based aqueous solution. As mentioned earlier, environmental polymers product, that is TIPART, is soluble in hot water. Once the polymer dissolves, the remaining solution consists of polyvinyl alcohol and glycerol. Similar to many photodegradable plastics, full biodegradation of aqueous solution occurs later through microbial digestion. The appropriate microorganisms are conveniently found in wastewater treatment plants. Procter & Gamble has developed a product similar to DIPART named Nodex PBHB. Nodex is an alkaline digestible, meaning that exposure to a solution with a high pH causes a rapid structural breakdown of the material. Biopolymer materials which disintegrate upon exposure to aqueous solutions are desirable for the disposal and transport of biohazards and medical waste. Industrial washing machines are designed to dissolve and wash away the aqueous solution for further microbial digestion. Finally, to conclude on this topic of biodegradable films and their mechanism, there are seemingly limitless number of areas where biodegradable polymers may find several uses. The sectors of agriculture, automotives, medicines and packaging all require environmentally friendly polymers. Because the level of biodegradation may be tailored to specific needs, each industry is able to create its own ideal material. Biodegradable polymers limit carbon dioxide emissions during creations and degrade to organic matter after disposal. Although synthetic plastics are a more economically feasible choice than biodegradable ones, an increased availability of biodegradable plastics will allow many consumers to choose them on the basis of their environmentally responsible disposals. The processes which hold the most promise for further development of biopolymer materials are those which employ renewable resource as a feedstock. Biodegradable plastics containing starch and or cellulose fibers appears to be the most likely to experience continual growth in their usage. Microbially grown plastics are scientifically sound and a novel idea, but the infrastructure needed to commercially expand their use is still costly and inconvenient to develop. Time is the essence for biodegradable polymer development, as society's current views on environmentally responsibility make this as an ideal time for further growth of biopolymers.